this video we're going to talk about what are called tree diagrams and Bayes' theorem. Tree diagrams are a very useful tool that help us visualize all possible outcomes, and we can do this with what you might call smaller sized variables or combinations of variables, and can't really do it when you get lots of big data that you're dealing with. So here is what we do here. Start with a contingency table. You'll notice here we've got two different variables, fund type and expense ratio. So a tree diagram helps us understand the marginal, the conditional, and the joint probabilities. So based on this data, we've got 21 bonds, 23 stocks, and 14 low ratio, 16 middle, and 14 high expense ratio instruments. So the tree diagram says, okay, here's the first branch. We've either got bonds and we've got stocks. So really you could draw a line going here to here and here. And then we're going to say, so this is the first variable, stock or bond. And then we want to say how many total instruments are there if we're going to break them down according to low expense, bond, expense type, and expense ratio, and type of instrument. So we'd say here's the first branch, and then that branches out. We've got low, medium, high, low, medium, high. And these probabilities are the unconditional probabilities, or the marginal probabilities. And so we would say, let's go down this branch here, and then we can go down the next branch, which says, given that we are a bond, what's the probability of a low expense ratio? And that's the conditional probability. And we can do that for each of these things. If we're going to go down here, let's say probability of a medium expense ratio given a stock, this probability is 0.391. So notice that the sum of these conditional probabilities add up to 1. This is true because we're conditioning on the same thing at each point. So given that we've got B taking place, that's the new universe, that's a new sample space. Everything that's going to take place is going to take place in B, so this probabilities had better sum up to 100%. And now if we want to find the joint probabilities, we know that the probability of the intersection is just the product of the one given the other times the probability, the unconditional probability or marginal probability of the other. So all we have to do is take this probability here, multiply it by this probability. So multiply those together, we get 25%. That's the joint probability. And if we come back up here, we would say this is going to be 11 divided by 44. Sure enough, that's 25%. So we do that for all of these things, and then notice that these probabilities also sum up to 1. And they'd better because they're random variables. So probabilities, remember, if you sum over the entire sample space, which is represented here, it's got to sum to 1. So this tree diagram is something that's very helpful when we talk about something called Bayes' theorem. And Bayes' theorem is a theorem that was invented by the Reverend Thomas Bayes, and he discovered that you can revise the probabilities given new information. So what he said is we have a prior probability or a marginal probability or an unconditional probability of some event, and we'll call it B, and we'll say how can we revise that given that we know that the event A has taken place, and that gives us what we call a posterior or a conditional probability. So Bayes' theorem says the probability of B given A is just the probability of A given B times the probability of B divided by the probability of A. Now this is really the same thing as writing, as we discussed previously, probability of the intersection of those things divided by the probability of A. But where this becomes powerful is when we don't know what the probability of the intersection is. We've got these conditional probabilities. So this is the prior probability of B. We're saying now that we know that A has taken place, now what's the probability of B? Oftentimes we are not given the probability of A, and we have to then calculate it. And if we do this correctly, we will get in the denominator probability of A given B times the probability of B plus probability of A given B complement times the probability of B complement. In other words, this denominator comes from the fact that the probability of A is just the probability of A intersect B plus the probability of A intersect, A complement intersect B. And so those are so those events, those two intersections, give us the entirety of the probability of A, and we can write that as the probability of A given B times the probability of B plus the probability of A given B. Sorry, that should be B complement, and that should be B complement up there, times the probability of B complement. We can generalize this even further if we have lots of different events that are collectively exhaustive. So we're referring to collectively exhaustive now. So the B's, all these B's here, B1, B2, and so forth, make up a collectively exhaustive partition of the entire sample space, and that allows us to write down the probability of A. And here's what a Venn diagram of this might look like. If we have B, here's B1, B2, B3, B4, B5, and B6, and we say here's the event A, then I can write A as just the intersection of this. So the intersection of A with B1, the intersection of A with B2, B3, B4, B5, and B6. So let's look at an example. We've got a hospital that has trauma centers, and I guess each hospital has a trauma center. So there's 3 hospital trauma centers, and these hospitals have malpractice lawsuits that come against them at a certain rate. And so we're going to say that B is the probability of the hospital. So B1 would be the probability that a patient is taken to or is operated on or sees a doctor in hospital 1, and B2 is hospital 2, and B3 is hospital 3. Then we're going to say A is the event of a malpractice lawsuit being filed. So we have a marginal probability for which hospital this person goes to, each person goes to. 50% go to the first one, 30%, and 20%. Notice these things add up to 1. And then we'll say given that they go to one of these hospitals, the probability of a malpractice suit is different at each hospital. So at hospital 1, it's 0.1%, hospital 2, it's 0.5%, and hospital 3, it's 0.8%. So hopefully you can see where this is going. We have marginal probabilities for each of the hospitals, and then we've got information about the probability of a malpractice suit. And we've defined event A and the BIs accordingly. So we're going to want to find the posterior probability of one of these hospitals given that there was a lawsuit. And to do that, we're going to take into account all the marginal probabilities and all these conditional probabilities. So sure enough, we're trying to find the posterior probability of someone being treated in hospital 1 in a trauma center given that they filed a lawsuit. So we can write that down. Probability of B1 given A, that's just the probability of A given B1 times the probability of B1 divided by the probability of A, which we can write as, notice this same thing is right here, so that goes into the denominator, plus the same sort of calculation for the other hospitals. So we just take all these numbers and plug them in. There's 0.1% times 50%. Again, that shows up here. We have 0.5% times 30%, 0.8% times 20%. Multiply all those things together, and now we get a posterior probability of about 14% for going to Hospital 1, given that there was a lawsuit. So how is that different? How does that differ? Well, what was the prior probability? Prior probability for B1 was 0.5. So given this information that there is a lawsuit, we can revise the probability or probability assessment of the event B1 taking place. And this is actually consistent with what we saw here, because people who go to B1 have much lower probability of filing a lawsuit. So in fact, they're you get 1.1%, 0.5%, 0.8%. None of these are very big, but it does happen, and we want to be able to revise the probability that they were at each of these hospitals. So we could do the same thing for B2. Say the probability of B2 given A, and that's going to be equal to, I got the same denominator, and the denominator turns out to be 0.0036. But now in the numerator I have 0.005 times 0.3. Okay, so whatever that turns out to be, we'll see on the next slide. But I can do the same thing for B3 as well. And here's what we get. Posterior probability is 13.8% for Hospital 1, 41.67% for Hospital 2, 44.44% for Hospital 3. So does that make sense? Yeah, it does, because Hospital 3 has the highest probability of a lawsuit of the three hospitals. And so this is Bayes' theorem, and this is extremely powerful, and is actually the basis for a lot of computing that's going on right now in business or finance or any other sort of place. Actually, just about every single discipline, academic or otherwise, is using, anyone who's using a computer wants to use this Bayes' theorem, or this Bayesian technique for statistics. So that's what we've got for this section of Chapter 5. There will be one more video about counting, and then possibly some videos about some example problems from the text. So we'll see you soon, and keep your eyes open for more videos. Send me an email if you have questions.